Welcome back to the second video for TEC 293 on Tuesday, March 23rd. In this video, we're going to finish up talking about heat treatment, and there are two specific things we have left to talk about. One is called a triple T diagram. It stands for time temperature transformation diagram. And the way you can think about that, it's really like a recipe. It's a diagram, but you can follow it like a recipe for when you're cooling down metals and you want to get a specific set of mechanical properties in your finished product. So to get that certain set of desired mechanical properties, you follow this recipe that will end up with the mechanical properties that you're looking for. That's a triple T diagram. The next thing we'll talk about in this video is the four basic processes that you can use for heat treatment. So we'll talk about hardening and tempering and normalizing and annealing. Those are the four most common heat treatment processes that you'll see anywhere for any type of metal. Like I said, it's not just steel, it's for any type of metal alloy. And so we'll talk through each one of those four basic heat treatment processes. So I'm going to go ahead and share my screen to start talking through my slides. All right, as I mentioned, the triple T, time temperature transformation diagram, they're kind of like a recipe, and they're going to tell us how fast do we need to cool down the material, or do we need to cool it down a little bit and then let it soak at that temperature for a while and then continue cooling it down. If you do that, you're going to get different mechanical properties, and some of those might be desirable. So for a desired set of characteristics, we can use the triple T diagram to tell us how to achieve those characteristics. So basically you just follow the instructions on the triple T diagram, kind of like following a recipe. All right, so they tell us like how fast we need to cool it down, or what should we do as we're cooling it down. One more thing I want to note here, it says this at the bottom here, there's a different triple T diagram for every single different steel alloy. So if you change the amount of carbon, it changes the triple T diagram. If you add more molybdenum to your steel, it changes the triple T diagram. So there's a different triple T diagram for every single different type of steel. All right? And we're just taking the type of steel and changing its mechanical properties through the way we cool it down. All right, so I'll show you a couple examples. Here is one triple T diagram. This shows four different ways that we can cool down this specimen. So initially, we're way up here at this temperature, and what we're going to do is we're going to cool it down, and this shows four different curves. So there's the red curve, curve 1, the green curve, curve 2, the blue curve is curve 3, and the tan curve is curve 4. And each of these curves specify a way to cool down this part. The red curve has us quench it really fast. And by the way, notice that the time is down here on the horizontal scale, and notice that the time is a log scale. All right, so this is not a linear scale, this is a logarithmic scale. So this is much less than 1 second. This is 1 second, 10 seconds, 100 seconds, 10,000 seconds, 100,000 seconds, and so on. So we're talking a fraction of a second to on the order of a few seconds here, to about a minute, to maybe a couple of hours here, to maybe a couple of days over here. All right, so what we've got is curve 1 is going to have us cool it down really quickly by quenching it. Curve 2 has us cooling it down really quickly, but only to here, about maybe 250 degrees Celsius, and holding it there for, looks like about 100 seconds, and then cooling it down. And curve 3 has us cooling it down to about 300 degrees Celsius, then holding it there for, I don't know how long that would be, somewhere between 100 and 10,000 seconds, so probably on the order of minutes to hours, and then cooling it down. And curve 4 has us only cool it down a little bit and then hold it at that temperature, and then after a long time, like on the order of hours, then finally cool it down. And when we do that, we'll change the grain structure of the material. So that changes whether we're going to get a lot of martensite or bainite and martensite or fine pearlite. So that's going to change the mechanical properties of the material. A lot of these, like curve 1, 2, and 3, they're going to give us more martensite. So these metals here are going to give us a harder and stronger material, but also more brittle and not as tough. Whereas curve 4 is going to give us a material that is not as strong and not as hard, but it's more ductile and it's going to be more tough. Here's another example of a triple T diagram. There's a bunch of different curves here, and you can see they all just do a different thing. So it depends on what your desired mechanical properties are, whether you're going to follow the purple or the blue or the green or the light blue curve. And they will all result in different mechanical properties of the finished product. In general, the slower you cool it down, the more of the equilibrium phases you're going to get, like ferrite and pearlite and cementite. And in general, the more equilibrium phases you get, the tougher and the more ductile your material is going to be, but it's going to be less strong, a little bit, and less hard as well. Conversely, the quicker you cool it down, like these curves over here, the purple and dark blue and even the green curve, when you cool it down quickly, you're going to get more martensite and bainite. That's going to make for a material that is stronger and harder, but also more brittle and not as tough. Nothing about this is going to change the density of the material or the elastic modulus of the material. All right, a few notes to think about. Think about your steel production facility, like we talked about a few weeks ago. They're trying to crank out as much steel as they can, right? They're trying to produce a bunch so they can sell as much as they can. And the fact of the matter is, they don't want to be spending hours to days slowly cooling down the steel they produce. Think about how much extra space they would need in their production facility to be slowly cooling this stuff down. So they don't want to cool down their steel really slowly. So generally it tends to be cooled usually just in air. Oftentimes it's called an air quench, is usually the way that steel production facilities cool down their steel after it's produced. And then after you purchase it, or after the metals distributor purchase it, then a further heat treatment can be applied for the specific component that you want to use, because you might want some specific mechanical properties of your specific component. So this is where the specific heat treatment applications come into play. So you might get a steel specimen from the manufacturer that has been air quenched, or maybe it was oil quenched. They'll do either one sometimes, but you want it to be especially hard or especially tough or especially ductile. And there are different heat treatment applications that you would apply for each one of those mechanical properties. All right, so we're going to talk about each one of these four. The first one, skip over that. The first one is just hardening. You can probably imagine what we're going to do based on what we've been talking about so far. To harden the material, well, we just want to get as much martensite and bainite in the material as we can. That's when it's going to make the material as hard as it can possibly be. So how do you do that? Step one, you heat up this specimen to a temperature above the upper critical temperature. That's the curved one. And then you cool it down quickly in water or in oil sometimes. And as a result, it's kind of like that triple T diagram, the curves with the really steep slope. You cool it down really quickly, and you're going to form a lot of martensite and bainite. And as a result, your part is going to be very hard. It's also going to be strong. It's also going to be brittle. For each of these processes, each of these four processes, there's going to be a two-step procedure. It's only 2 steps. They're not that hard. But I would expect that you would know these 2 steps for the purpose of a quiz or an exam. So make sure that you're familiar enough with these 4 processes that you know the 2 steps to do them, and then also what the result is going to be. Like, why would you do hardening? Well, it's if you want a material that is really hard. You know, maybe you're going to use this for a surface that's going to come into contact with a lot of friction or wear, and you want it to be very wear resistant. That'd be a good reason to do some hardening because a harder material is more wear resistant. The next one we'll talk about is tempering. Tempering is all about toughness. So remember the T sound, tempering, toughness. Toughness is what is going to be given to you by the tempering process. What it tries to do is change a lot of the martensite or bainite that might be in the material to ferrite and perlite and cementite, those equilibrium grains. So what you want to do, you want to heat it up again because you got to get that recrystallization process to happen. So you got to heat it up to a little bit below the lower critical temperature. That's the flat one that's at 1333 degrees Fahrenheit. Heat it up a little bit below that and then let it cool relatively slowly in room temperature air. So you just set it out, you know, in air and let it just cool naturally in air. And naturally, it's going to cool down more slowly than if you dunk it in water or something, or even blow cold air at it. Just let it at normal room temperature, let it cool down. That's what tempering is. All right, so what's going to happen there with tempering? It's going to be pretty strong and it's going to be pretty ductile. And as a result, it's going to be quite tough. So the whole purpose of tempering is to get a specimen that is quite tough. How tough? How tough is it going to be? Well, that is a great question. I'm glad you asked. We are going to measure toughness testing through impact testing. And we'll talk a lot more about that next time. But basically, we're going to break them and we're going to measure how much energy was absorbed by the part as it broke. And that is the definition of toughness. The definition of toughness is how much energy does it absorb before it breaks. So we're going to do exactly that in the second half of Lab 7, coming up in just a week or two. The third one is normalizing, and normalizing is named kind of confusingly. When you say that you're going to normalize something, you probably have in your mind you're going to return it to its original state, right? That's what normalizing might mean. But this is actually different. That's actually not what normalizing means in this context. Another way to normalize something, if you're another meaning of that, means to make it standardized. To normalize something is to make it standardized in relation to something else. That's another meaning of the word normalizing. It's more of the meaning in the context of like mathematics or science. If you're normalizing something, you're comparing it to something else and making it relative to something else, standardizing it. And that's actually what we're doing here. The purpose of normalizing is to make the grains consistent and uniform. All right, so what can happen in various manufacturing processes like forging, where you hit the part with a big, huge, tons of force and you form it into some part, or the rolling process where you're compressing it and squeezing it into a different shape. What happens is you deform the grains themselves in the part. So your grains are kind of squished and they have different dimensions in one orientation than they do in another orientation. And that affects the mechanical properties of the part. So if you want to make the grains uniform again and make them a standard size, that's when you would apply the normalizing heat treatment process. All right, so we're making the grain size more uniform. We're also removing some of the coarse grained structures. And the way you do this is you heat up the material 100 to 200 degrees Fahrenheit above the upper critical temperature. This is actually the hottest one. This is the one that gets the material the hottest. And then you let it cool in air at room temperature. So the difference between this one and tempering, they're pretty similar actually, but this one you get the material hotter. This one you go way up above, a couple hundred degrees up above the upper critical temperature. Contrast that with tempering, where we only went a little bit below the lower critical temperature. All right, so the results from the normalizing procedure is you get a uniform grain structure where the grains are approximately all the same size, and that gives more uniform mechanical properties to the material. The last one we'll talk about is annealing. The big thing about annealing, it makes the part more ductile. All right, and a really common application for annealing, let's say you've already done some work on a specimen. Let's say you've taken a piece of metal and you've forged it into a different shape, or maybe you've roll formed it into a different shape. And in the process, you've done work hardening. You know, when you forge something or roll something, you have done work hardening because that's plastic deformation. And so if you continue to do that repeatedly, if you take that specimen and forge it, and then put it in a different forge and forge it again, and then put it in a different forge and forge it again, or roll forming, if you go through many steps in the roll forming process, eventually you're going to get so much work hardening on that material that it could break, that it could fail. All right, so much plastic deformation that it could fail. So what you want to do to avoid that failure is somewhere in the middle of that process, you know, send it through some of the roll forming stages or send it through some of the forging stages, but then pull the specimen out and then do an annealing process on it to restore its ductility, and then put it back into the process, and then you can do some more roll forming or some more forging on it. You can plastically deform it again without it breaking. All right, so the annealing is all about ductility. It's to increase the ductility of the part. Also, that's another way of saying it reduces the internal stresses, you know, the work hardening that builds in stresses to the specimen. The way you do that is you heat it up above the upper critical temperature, but not quite as hot as the normalizing process that we just talked about. You heat it up about 75 Fahrenheit above the upper critical temperature. And then this is really the key part. With annealing, you cool it down really slowly. Generally, for most people, the best way to do that is to take the specimen, put it in the furnace, and then heat it up to this temperature right here. And then the best way to do step 2, leave your specimen in the furnace and just turn the furnace off. Don't take it out of the furnace, just leave it in there. And then what's going to happen is gradually over, you know, a day, over the course of about a day, the furnace is going to gradually cool down, and the specimens that are inside the furnace will gradually cool down over that time. And that's actually what we're going to do in Lab 7 for the part that we anneal. We're actually just going to leave it in the furnace, and we're going to turn the furnace off, and we're going to let it gradually cool down, and we'll pull it out of the furnace the next day. All right, so this has been quite a lot of material today. We talked about equilibrium diagrams and equilibrium phases, as well as non-equilibrium phases like martensite and bainite. And then we talked about our triple T diagrams that are kind of like the recipe for achieving a certain type of finished product with desirable qualities. And then we talked about these 4 specific heat treatment processes. So for those, make sure you know the purpose of that process, what it does to the part, and make sure you know the 2-step procedure for how to apply it. There's some supplementary materials, mostly just some pictures of perlite and bainite and things. So that's all in there. There's some videos that are kind of helpful, but I'm not going to show them in class. So you have access to these slides. You have access to all the slides, so you can take a look through those if you want. But that's going to wrap up the material for today. In the next class, we're going to talk about impact testing. And that is going to be useful for us in the next lab, because you are going to do impact testing in Lab 7. So we're going to talk about that. Impact testing, as well as we'll talk about Lab 7, how we're going to do Lab 7. We'll talk about that in the next class. All right, so as always, let me know if you have any questions, and I'll see you next time.